Morning.
Okay. So it's my pleasure to introduce Jurij Volčič, our very first virtual colloquium here at UF. He's going to tell us about positivity of polynomials in matrix and operator variables. So take it away, Jurij.
Okay, thank you, Scott. Thanks for inviting me. So I'm going to be talking about, well, positive polynomials, right? So because they are going to be in matrix and operator variables, it's kind of going to be some kind of a non-commutative inequalities. So the point of this talk is mostly to do like a review of results and also kind of to compare what works for matrix variables, what works for operator variables, when are one of them better than the other. Okay, now, since, I don't know how much you know about positive polynomial classically, so let's just start at prehistoric results, like classical commutative setting. So this X underline, that's just going to be, commuting variables. And I'm going to say that a polynomial with real coefficients, multivariate polynomial, is positive if it's always non-negative no matter what kind of a tuple of real numbers do I plug in. I should probably call this non-negative polynomial, but that's a little bit of a mouthful, so I'm going to call it positive one. Okay, and then we have some obvious examples of such polynomials, right? And so if I take a square of a polynomial, of course, whatever I plug in, it's going to be positive, well, non-negative. And vice versa, if I take sums of squares, it's going to work the same, right? So, and that's what we call them, these sums of squares. So if I take sum of square of polynomial, well, this polynomial is going to be always, it's going to be positive. So whatever I plug in, I'm going to get a non-negative number. So if you want, this is kind of a geometric picture. So being positive, and this being sum of square, that's kind of algebraic picture. So being sum of square implies being positive. Now, what about the converse, right? And that's like a old result. I think they say that it's Gauss's result. I don't know. It's super old. We don't actually know when it was. So that's actually the case when you have univariate polynomials. So if I have just polynomials in one variable, then if I know that it's positive, then I know that I can write it as a sum of squares. Actually, you can write it as a sum of two squares. You can give that to, I don't know. So it's an exercise for students, right? So if you have a positive polynomial, well, it has real coefficients. So that means that zeros they are complex and they appear in pairs. So they are real zeros, but because it's positive, every real zero needs to appear with an even order, right? And this is kind of the information that you need to rewrite your polynomial as a sum of squares. Okay. So that's univariate polynomial. And then, this kind of picked up speed around 1900, when Hilbert asked this question for a general multivariate polynomial. So if I have a multivariate positive polynomial, can I write it as a sum of squares of polynomials? And Hilbert already he had a non-constructive proof that that's not the case as soon as you have two variables or more. Now the proof was non-constructive, so it kind of took almost 70 years till Motzkin came and showed that, this concrete polynomial, it's positive, but it's not sums of squares. Can't be written as sums of squares of polynomials. So here's the graph of this polynomial. It's not too hard to convince yourself it's positive. So when you're looking at these three terms and then you compare this negative term here, you see that this should kind of remind you a little bit of some kind of a arithmetic inequality, arithmetic mean of something. Well, if I would divide everything by 3, these three first terms would be arithmetic mean of something, and this would be the geometric mean of something. So it boils down, this polynomial is positive, it boils down to that inequality between geometric and arithmetic mean. Okay, so it's not the case. So that's, Hilbert already knew that in 1888. And then in 1900, right, or when was that, when he set up the list of the famous problems, the 17th problem asked, I can't really write every positive polynomial as a sum of squares of polynomials, but maybe can I write it as a sum of squares of rational functions? Kind of you add a bit more freedom. So basically he asked the following. So if you have a positive polynomial, can I then find two polynomials, p and s, such that s is a sum of squares, and such that p squared times f is this sum of squares polynomial. So, and this is indeed the case, so that's true. So Artin proved that almost 30 years later. So Hilbert's 17 problem is one of those that has a positive solution. And this is kind of a, so being positive, as I said, I want to think of that as a geometric property, and now this is now the algebraic property that it's kind of equivalent, right? Because if I have two polynomials p and s with s being a sum of squares such that this relation holds, well, then that tells me that f is positive, right? Because this is always going to be positive, well, apart from whenever p is 0, but that doesn't happen often, right? And this is also going to be something positive, so f needs to be positive. It's quotient of two positive things, right? So Moleskine can't be written as a sum of squares of polynomials. However, the way I write it here, Moleskine polynomial, so this purple thing here satisfies the following relation. And from here, you can basically read out that, okay, I can write it in this form because, well, I see that there's lots of some squares around. Well, you can really, using this equality here, you can provide a description like that. Right? So Hilbert's 17 problem, or maybe more Artin's solution, Artin techniques, that was kind of a breakthrough for what we know nowadays as real algebraic geometry. So real algebraic geometry, because we're kind of looking at some correspondence between geometry and algebra, but we're looking at everything over real numbers. And because we work over real numbers, we talk about inequalities, so that's called real algebraic geometry. Okay. So in general, so real algebraic geometry, okay, we know now how polynomials that are positive look like, right? But then what we often kind of care is, well, maybe I don't care about polynomials that are positive everywhere, right? But maybe I want to constrain some sets in R to the D and just talk about polynomials that are positive there. So what I'm saying is, well, real algebraic geometry really studies positivity subject to constraints, okay, to polynomial constraints. So let's pick some set of constraints, a bunch of polynomials. And to this bunch of polynomials, we're going to assign the set of points. So these are all real points where all these polynomials from C are positive. So, for example, if I have D equals 2 and I take, what do I need to take? I take, I know, 1 minus x1 squared minus x2 squared. This being bigger or equal to 0 means that I'm describing a disk, a unit disk. And in general, we call that, so if C is finite, and usually we think of finite sets of constraints, C is then called a semi-algebraic set. Semi-algebraic because it's given by polynomial inequalities, not by arbitrary inequalities. Okay, so these are the geometric objects, right? So sets in the space, in affine space, in real affine space or vector space, if you want. That's the geometric side. And you know, before I was saying, well, sums of squares are the obviously positive things. Now I want to talk about, well, what are the obviously positive polynomials on sets like this? Like what kind of a polynomials are obviously positive on KC? Well, sums of squares are positive everywhere, so okay, that's great. But maybe I need some more, right? And then whenever you take a polynomial of the following form, so some sum of squares of polynomials plus sum of squares of polynomials times a constraint, and so on, whenever you take this kind of a, I mean, it's not quite linear combination, but such a sum, this is obviously positive here, right? I mean, because, well, if I take a point from here, I plug it in, well, each term is going to be positive. And the set of such polynomials, that's called the quadratic module generated by C. Why do we call it module? I mean, that's kind of like a terminology from algebra. Because I can, instead of giving you this concrete description, I can also have an alternative description. What's QC? So that's a smaller subset of polynomials that contains C, that also contains the number 1, the constant polynomial 1. It's closed under addition, and it's closed under multiplication by squares. So if you want, these are three, I mean, these two are two operations that preserve positivity, right? If I have two things that are positive, well, then the sum's also going to be positive. If I have something positive times a square, well, square is obviously positive everywhere, so that's again going to be positive. Okay.
So one question, why did it take so long for them to come up with that concrete counterexample or whatever?
Yeah, good question.
It seemed like a relatively simple looking polynomial.
Exactly. Yeah. Once you know what you look at, it's like I mean, proof of being positive takes a line, and proof of not being sums of squares takes 4 lines. I agree. It's a very simple polynomial, but it's one of those things that it's easy once you have it.
Okay, thank you.
So it's kind of, so yeah. I don't really have a better reason. It's also, it's kind of it's a minimal counterexample in some sense, because if you have a bivariate polynomial of degree 4, then you have that it's going to be positive if and only if it's sums of squares. So degree 6 is really the first time when things go wrong.
Let me just jump in on this. So is there a constructive algorithm that, given a polynomial, multivariate polynomial that's non-negative everywhere, constructs the type of proof you just showed, constructs a multiplier?
So, not quite. So the thing is, it exists. I mean, you can get up you can get an algorithm if you're lucky that your polynomial has a non-negative minimum or non-negative infimum. Sorry, non-zero infimum, right? So if you have a polynomial that it's like strictly positive, and you kind of then you know, like, estimate of how far away from zero it is, then you have an algorithm. Yes.
Yeah, but the polynomial you showed there, in fact, does take 0 at 1, 1.
Exactly. Yeah. So for this one, I mean, this.
It touches the plane, I think, at that one point.
Yeah. This polynomial is still. No, but okay, I should say like that. I mean, for this one, actually, I don't have a proper algorithm. I mean, this was like making this representation that I gave you. That was, I pulled it out of the head. I don't think you can get this one automatically.
So are there any polynomials where it's not known? It's known that it's not negative everywhere, but no one has this kind of, but no one has a construction that writes it as a sum of squares of rational functions?
So like you're saying, okay, it's positive. We know that it can be written as rational functions, but we don't know any representation.
Right. There's no representation known.
Yeah, I don't think there. So I think for all the concrete examples that people looked at, eventually they managed to find.
Okay. Thank you. Thank you.
But this is, I mean, that's a fair question, right? I mean, as you see, I mean, yeah, that's related to the fact that checking positivity in a global sense, like being positive on all tuples of real numbers, in a sense, it's a hard problem, right? And we're going to see that when we talk about the constraint situation, that's sometimes better, right? Okay, so now here I showed you. Okay, so this is the kind of a positivity set of constraints. These are obviously positive polynomials, and you're not going to be surprised if I tell you that, of course, there are polynomials that are positive here, but are not of this form. I mean, it's not surprising. We already know that this happens when C is an empty set. When I just talk about global positivity. However, we have some better result whenever this constraint set KC is bounded. Actually, we need slightly more. So we say that a quadratic module is Archimedean if there's a positive number rho such that rho minus xi squared lies. This polynomial belongs to this quadratic module. Okay, so it's an algebraic property, but what does it tell us? So I mean, if I have an Archimedean module, so that means that these things are positive on my set. So that means that tells you that KC is bounded, right? I mean, it's bounded by, well, it lies in the hypercube of square root of rho, right? And vice versa, if I have a bounded set, well, then I can always just add this bound. I can always just bound appropriate. I can always just add this kind of terms to the constraint set, and I'm going to get a quadratic Archimedean model. So this abstract algebraic property basically tells you that you're dealing with a bounded constraint. And now for bounded constraint set, we have a result kind of a slightly in a different direction. That's due to Putiner, much younger. So if I have an Archimedean module, basically that corresponds to the underlying set being bounded, then checking if f is positive, is non-negative on this bounded set, that happens if and only if for every epsilon, f plus epsilon lies in the quadratic model, meaning that f plus epsilon can be written as a sum of squares plus sum of squares times constraints. I should point out that f plus epsilon lying in quadratic module for every epsilon does not imply that f is going to be in quadratic module. So these quadratic modules, of course, they have some kind of, well, they have a topological structure, right? And they are usually not closed. So that's kind of a problem here. So somehow I get a different kind of a result, right? Instead of talking sums of squares with denominators, I'm talking now about sums of squares for every epsilon, right? And now I know if this result looks nicer than previous or not, but that's probably one of the most used results from real algebraic geometry. And now the reason is polynomial optimization. So maybe, I mean, even if you're going to doze off for the rest of the talk, that's maybe something, a little bit of a story. That's why we care about this sums of squares and whatnot. So let's say that you choose some polynomial, you have some finite number of constraints. Let's suppose that the quadratic module is Archimedean, so bounded set of constraints. And now let's say that you consider the optimization problem, so find the maximum of f on this set. Okay, so this is a closed set, it's bounded, so it's compact, so this maximum really exists. Okay, so now I'm gonna change this a little bit. So looking for the maximum of f, that's well looking for the minimum of u of the smallest possible mu, such that mu minus f, so this is a polynomial, it's positive on Kc. Now, being positive, well, being positive, non-negative on Kc, we just saw that we can describe that with Putiner's theorem, right? I mean, there's some epsilons happening, but since I'm looking here for minimum or infimum, those epsilons run away. So what happens is that this number, this maximum, it's actually the same as saying, well, let's find the infimum of mu such that mu minus f lies in the quadratic module. So this is now kind of we're going away from, well, from geometry, we're going to algebra. So we want to represent mu minus f as a member of this quadratic module. And then you go even a little bit further. So being in a quadratic module means that, okay, it's a sum of squares plus sum of squares times constraints and so on. And then you say, well, first I'm gonna restrict myself and I'm just gonna allow sums of squares that have degree less than 2n for some n. Right? So kind of for each n, you can kind of bound the degrees and you're solving this problem. Now, of course, the bigger n's that you're going to allow, the bigger degrees of these sums of squares you're going to allow, the better approximation you're going to be getting of this number here. Right? So eventually, I mean, there's some theory that tells you, okay, how fast it's even going to converge from here to here. And now the thing is, okay, maybe this looks kind of nasty, but that's something we can actually efficiently compute. I mean, it's kind of a finite dimensional problem now that I bounded the degrees of sums of squares. And this is something that can be efficiently computed using semi-definite programming. I'm not going to explain what semi-definite programming, I mean, it's not even my, I mean, yeah, it's not, I'm not even that, I don't use it that often. But if you've heard of linear programming, that's a generalization. Okay. And we have all this like interior point algorithms for it, and it's implemented in MATLAB. There's few packages. Also, the latest Mathematica has packages for solving this kind of problem. So the point is checking positivity. So that's kind of our geometry. It's a hard thing, but then checking if something can be written as a sum of squares of polynomials, that's easy. That can be done efficiently. When I say efficiently, it's polynomial time algorithm. Okay. So this is kind of also related to the, it's kind of related to the fact that, before when we were asking about, so global positivity, when you have denominators, that's kind of a more annoying, but this like bounded positivity, when you don't have denominators, you just have that epsilon flying around. It's this is kind of easier, okay? So this was kind of the classical situation, so global and constrained version. And now I want to talk about this kind of certificates of positivity. So how sums of squares guarantee positivity. I want to talk about that for matrices and for operators. Okay, so I need to appropriate my notions here a little bit. So instead of numbers, I'm going to be talking about matrices or bounded operators on some Hilbert space. Now, among numbers, well, the real numbers, what's the corresponding notion on the operator side? Well, these are the self-adjoint operators. So I'm usually going to work on real Hilbert space. So if I talk about matrices, that means that I'm going to be talking at symmetric matrices. So why is that? Real numbers, we have ordering, right? We can order them. We can talk what's bigger, what's slower. Well, you can do something similar for matrices, right? For symmetric matrices, because, well, eigenvalues are real, right? So you can talk about positive matrices, meaning eigenvalues are non-negative, right? So instead of being positive, now it's going to mean being positive semi-definite. And now the obvious thing, before the obvious positive thing was a square, right? Square of any number, of any real number, it's positive. And now, well, because we're going to be dealing with arbitrary polynomials and sorry, not polynomials, matrices operators. Well, we're going to talk about Hermitian squares. So A times A star is going to be the obviously positive semi-definite matrix or operator. Okay, so that's kind of a dictionary between classical commutative stuff, numbers, versus now that we're going to start talking about positivity of matrices and operators. Now, of course, matrices operators, they don't commute, right? So I need to change my polynomials a bit. And well, I'm just going to say that, well, I'm still going to have variables from x1 to xp. So these are going to be my arguments. It's just that now I'm going to forget that they commute. So what does that give you? Instead of polynomials, you get, instead of polynomial ring, you get so-called free algebra. And the elements of it we're going to call free polynomials. So basically, these are just polynomials in letters. It's just that now x1 and x2, they don't commute, right? I can't put all the x1s on the one side and x4s on the other side. So it's kind of, if you want, free polynomials are just linear combinations of words in my letters. Now there's something that we have now that we didn't have for commutative polynomials. I'm going to start talking about also about involution. So I have a natural involution on polynomials, on free polynomials. Namely, the natural involution is going to, I'll take the one that fixes the variables. And if I apply it to a monomial, to a word, if you want, it's going to reverse the order. So kind of I'm simulating the involution on matrices or on operators. So if I have self-adjoint matrices, if I have a product of self-adjoint matrices, the products, of course, it's not necessarily going to be self-adjoint, right? And if I take the conjugate, well, what's going to happen is just multiplying the matrices in the other order. Okay, and so now these free polynomials, because I have arguments that don't commute, well, now I can evaluate that on tuples of operators on a Hilbert space, for example. So if I have a polynomial like that, so and I take some pair of operators on the same space, well, then what's evaluation? Well, I just replace the first symbol with the first operator, second one with the second operator. Whenever I see just a constant, I replace that by identity operator. So I get the result is then an operator. And now if I take a polynomial that's preserved by the involution that I described on the previous page, and I take a tuple of self-adjoint operators, then the result is also self-adjoint. So that means, especially when I'm going to talk about matrices, usually I think I'm mostly going to talk about matrices later on. But so it's self-adjoint, so we can start talking about, is it positive semi-definite or not, positive or not. And now here, I mean, when you talk about the classical setting, well, you just plug in real numbers and that's it. And here we're kind of going to consider like three different scenarios. Either we're going to be checking positivity of this kind of functions, for example, just on symmetric matrices of a fixed size. Or sometimes we're going to consider positivity of such expressions for all symmetric matrices. And sometimes we're even going to allow operators. So you see, it's kind of so when you go down, you're going to a stronger and stronger property. If something is positive for all self-adjoint bounded operators, then it's also going to be positive for all symmetric matrices. And if it's positive for all symmetric matrices, it's also going to be positive for some particular size. So these are the three settings that I kind of want to compare. Like we'll see that for some questions we have better answers to 1, for some questions we have a better answers for 2, and so on. And as in the commutative setting, we're kind of compare two types of results, either global positivity or some kind of a bounded positivity. So global positivity, for example, really positivity on all symmetric matrices, and bounded positivity, for example, we're only going to consider positivity on, I don't know, contractions, right? That's like some subset of matrices. So maybe just an example, like what I want to talk about. So consider the following bivariate NC polynomial, free polynomial, I should call it free polynomial. Okay. Looks something complicated, right? I mean, plenty of terms, like what's that, 7 terms. And I'm actually going to modify it a little bit. I'm going to take now polynomial f, which is just g of x1 squared, comma x2. So I could just write here x1 to the 6, x1 squared, x1 4, and so on. So this polynomial, well, both of them, f and g, they are self-adjoint. I mean, they are preserved under involution, because you see every term that I have, for example, this term here, oops, I also have the corresponding transpose, if you want. Okay, so that means that it's self-adjoint function, if you want. So whenever I'm going to be plugging in something self-adjoint, it's going to output something self-adjoint. So we can start talking about whether or not the output is always positive or not. And for example, for this concrete choice of f, you'll have to trust me on this one. I mean, I'm not going to prove it now, but if you plug in any pair of 2 times 2 matrices, the result is always going to be positive semi-definite. On the other hand, if you plug in these 2 symmetric 3 times 3 matrices, and you can really, well, just take these 2, you plug it in F, you're going to get something that's not positive semi-definite. So it has some negative eigenvalue. Okay, so that's why I'm going to, for example, say that this polynomial f, it's positive on 2 times 2 symmetric, on 2 times 2 symmetric matrices, also in particular also on 1 times 1 matrices, or just numbers, but it's not positive on 3 times 3 matrices. Okay. So maybe a little bit of a commercial break. I mean, why do we do that? I mean, so there's a couple of topics that kind of deal with this kind of matrix inequalities, operator inequalities. Maybe you recognize yourself in one of these. I mean, you also have, of course, experts in your own department. So James, Scott, Mike, right? I mean, work on monotone functions, convex functions. So I mean, it's matrix monotone, matrix convex. So I mean, there's inequalities lurking around. So it's, I mean, we're not doing that. I mean, just for the theory, there's ostensibly some applications behind. Okay. Okay, so now we described, well, I described what are my functions. I'm going to be talking about, well, I said what means to be positive, what kind of a positivity am I going to look at. Now let me also say, well, what are now the obviously positive things? Well, in the commutative setting, sums of squares of polynomials were positively obvious. Well, now I'm not going to take squares because, you know, square of an operator is not, it's not even, I mean, square of an operator, it's not even self-adjoint if operator was not self-adjoint. So I'm rather going to take polynomials of the form p times p star, right? Because here, whatever I'm going to plug in, I'm going to get something positive semi-definite plus so on plus positive semi-definite. So if you want, these are now the obviously positive free polynomials. Now, as I said before, we're also going to talk about the constraint set. So I mean, if I take some collection of polynomials, I can talk about their positivity sets. And as I said before, I'm kind of going to consider three settings, right? Either I'm just going to look at matrices of some particular size, or I'm going to look at all matrices, or maybe at operators. So that's why I'm going to define three different sets. So this key as K, C, N, these are going to be tuples of n times n symmetric matrices that make these constraints positive semi-definite. And then the union of all of these sets, so that's kind of a like disjoint union of such sets, that's going to be called K-fin. So kind of I'm looking at all matrices of all finite sizes, satisfying the constraints. And then finally, I'm actually also going to look at this K infinity. So these are, so I should write here this H, it's, I don't know, any infinite dimensional Hilbert space. So I'm looking at all the self-adjoint operators that make these constraints positive, semi-definite. So these are going to be kind of my substitutes for semi-algebraic sets. Now, before I had quadratic modules, so there were some sets of polynomials that I said, oh, they are obviously positive, right? And here I'm going to have something similar, right? So if I take, for example, if I take any constraint and then I multiply it on the left-hand side with some polynomial p, on the right-hand side with polynomial p star, then this kind of a stuff is going to be positive whenever I plug in some x like that. And then I can take sums of these kind of guys. Like I can take sums for different constraints, for maybe different side polynomials. And this is, now I'm just gonna, to save memory, I'm gonna just call this quadratic module again. So again, as before, I have an alternative description. So I mean, what's that? It's the smallest subset of polynomials that's, well, contains the constant polynomial 1. It's closed under addition, and it's closed under this kind of a squaring, if you want. So if I take obviously positive polynomial and I multiply it with p and p star, well, when I plug some matrices in it, well, that's still going to be obviously positive, right? Because you're just conjugating from the signs, right? It's not gonna change the signs of eigenvalues. If the eigenvalues were positive before, they still stay positive then. Okay, so I'm gonna address these three settings. So these two settings, one kind of, I look at all sizes, and the infinite dimensional case. These two are slightly, well, I mean, better behaved than this one when you look at the fixed dimension. Maybe that's kind of a surprising, or maybe it's not. So maybe let's first fix on this middle situation. And we get the following result. So that's a result now 20 years old from Scott, and at the same time from Bill Helton. And this is kind of the result that kickstarted all this non-commutative theory. Well, this is the one that I'm describing. So if I take a free polynomial, then and I start plugging in symmetric matrices, then the result is always going to be semi-definite, if and only if I can write this polynomial as a sum of Hermitian squares of polynomials. So it's kind of a global version of, well, it's a global thing because I'm just plugging in all matrices, no constraints. And this is kind of the non-commutative version of Hilbert 17 problem, right? Hilbert 17 problem said, oh, positivity when you plug in numbers, real numbers, and now I'm plugging in symmetric matrices. But this kind of looks even stronger than that conclusion, right? There's no denominators here. It's just sums of squares, well, Hermitian squares. So it's, in a sense, it's I mean, more elegant result if you want. It looks like a stronger result, but the thing is, I'm asking for more here, right? I'm not just asking for positivity on numbers, I'm asking for positivity on all matrices. And that's kind of a typical for whenever you ask something to happen in all dimensions, it's kind of a you ask for more and you get more back. Okay? And for these polynomials, now you can actually efficiently check. If you give me a polynomial f, I can use semi-definite programming, what I described before. I have an algorithm to check if I can write these polynomials as a sum of squares of polynomials. And if I can, well, then it's positive semi-definite for all the input, otherwise it's not. Okay, and actually, you can even find some bounds. I mean, here I'm talking about positivity on all matrices of all possible sizes. Actually, it always suffices to just check large enough n. This n depends kind of exponentially on the number of variables and on the degree of the polynomial. But it's kind of, I mean, it's you don't actually need infinitely many sizes. You can check finitely many sizes. So that's kind of a free analog of Hilbert 17 problem. Now, when you go to the constraint setting, you have something similar as Putiner before, right? So if I have a kind of a bounded constraint set, so bounded again, I have this kind of Archimedean condition, same as before. You don't even want to think about it too much, but kind of a boundedness. Then you have the same condition. So being, well, same condition. Being positive semi-definite on the set of all operators satisfying some constraint, it's equivalent to f plus epsilon being a member of the quadratic module for every epsilon, right? So meaning that f plus epsilon can be written as a kind of a sums of squares, can be certified as a sums of squares. And here is already one thing when I said, well, I want to keep a little bit of a distinction between matrices and operators. Here I really, in the assumptions, I need to assume positivity on operators, on infinite dimensional Hilbert space. So just using matrices, it's not going to work. And the reason is just that if I allow like super crazy constraints, it might just happen that there's no matrices satisfying those constraints, but there might be operators satisfying those constraints. And that's kind of I mean, you kind of make up these examples. I mean, like you start with some universal C-star algebra that doesn't have finite dimensional representations, like Kuhn's algebra, and then from this Kuhn's algebra, you can kind of make up constraints that there's no matrices satisfying that, but there's going to be some operators satisfying that. So that's why, in general, you want to keep a distinction between matrices and operators. Now you can skip this distinction if you add the geometric property. So not just that you want your set to be bounded, but if you also assume that it's convex. I didn't really explain exactly what's convex, but I mean, think of, for example, set of all matrix contractions. That's a convex set because if I take two tuples of matrix contractions of the same size, and if I add these two tuples together, again I get a tuple well, if I take a convex combination of it, I'm going to get again a tuple of contractions, so convexity. So whenever you have a convexity, then checking positivity is actually equivalent to checking whether or not something isn't in the quadratic module. So it's even better than, well, the conclusion is even stronger than the classical Putiner because I don't even need any epsilons anymore. Okay, so you see that kind of whenever I consider positivity on matrices of all sizes or maybe on operators, I kind of get the same, well, same results as classically. The proofs are quite different. The classically, I mean, that's real algebraic geometry. This is more like functional analysis. But whenever I kind of whenever I don't put any constraint on the size of matrices that I'm going to be plugging in, everything kind of plays nice. Okay, now let me look at the same questions, but now I'm going to fix the dimension, right? So I'm going to look just at matrices of a fixed size n. Okay, and then this was first addressed by Procesi and Schacher, two algebraists. And they formulated the following conjecture, so that if I fix a size of matrices n and I take a self-adjoint polynomial, free polynomial, then this polynomial is going to be positive semi-definite on all matrices of symmetric matrices of size n, if and only if I have this kind of a relation. So here P, S, and P0 are again free polynomials. S is a sum of Hermitian squares, and P0 is a polynomial that's constantly zero on n times n matrices. So if you forget about P0 at the moment, right, then this just looks like what we saw in Hilbert 17 problem, right? It's just kind of a sums of squares with denominators, right? P is kind of a denominator. But then because I just talk about positivity on n times n matrices, then of course there's no reason that F can be written as a sum of squares with denominators because I just have information for n times n matrices. So kind of I can write it as a sums of squares modulo an identity on n times n matrices, right? So the thing is, in one direction is again clear. If I have this kind of a relation, then it's easy to convince myself that F is going to be positive, semi-definite, no matter what I plug in. Now, what about the other way around? Now, it works for n equals 1. Now, what's n equals 1? Well, symmetric matrices of size 1, these are just real numbers, right? So that's just the classical Hilbert 17 problem, right? It's also true for n equals 2, so that's what Procesi and Schacher proved in 76. However, it's false for n equals 3. So there's a polynomial that's positive on all 3 times 3 symmetric matrices, but I can't certify that with sums of squares of free polynomials. And well, I didn't write the concrete example down. It's, I think, something of degree 15. I think maybe one can get even lower than that. So we proved that, what was that, 2 years ago. We don't know what happens for bigger n's. Now I think it's fair to think that it's probably going to be, conjecture is going to be false in general for most n. There's some algebra behind that makes us slightly skeptical about what happens for powers of 2. So I'm not sure exactly what's going to happen for n equals 4, if it's going to be true or false, but that's kind of the smallest case when I don't know what to answer. So that's kind of the global situation for matrices of fixed size. It's kind of a tricky. On the other hand, if I'm in a bounded situation, again, I'm not looking at all symmetric matrices, but symmetric matrices satisfying some boundedness conditions, like Putiner's positive shear sets, then I get a nice result. So I fix an n again. I fix some constraints such that they give me a bounded set of matrices. Then checking if a polynomial is positive semi-definite on that set of matrices, that's equivalent for every epsilon I can write f plus epsilon as something from the quadratic module plus something that's going to be constantly zero on n times n matrices. And that's true for all for all natural number n. Right? As opposed to the global case, when we saw that it kind of plays nicely just for n equals 1 and 2, and then breaks down for 3, this works for every fixed n. Okay, so kind of now when you look back at this one, the conjecture that breaks down, so what's the problem? Kind of sums of Hermitian squares are not enough. I mean, they certify positivity, but it seems you're missing something. So you're missing some additional structure that's going to bring you positivity. And that's actually what Procesi and Shachar already figured out, that we need something more. We need to extend our set of functions a bit. So instead of just polynomials in variables x and 1, I'm also going to take into account traces of polynomials. So I first define pure trace polynomials. These are just trace symbols of words, right? So I just take, so these are, if you want, commutative symbols. For example, look at this one here. Right? So these are pure trace polynomials. And then I say, okay, then I also allow for the normal free polynomials, and then this all together, this all functions of this form, that's what I'm going to call trace polynomials. So you kind of take free polynomials and you add their traces. So we extended the family of our functions a little bit. Now, these trace polynomials, I mean, they originated, yeah, around in 70s, right, in invariant theory. Well, what's the point? So traces are invariant for basis change, right? If I have a x1, x2, two matrices, and then I make a basis change, like I multiply with p inverse both matrices, and trace is going to stay the same, right? And Procesi showed that actually every polynomial function that you have from n times n matrices to n times n matrices, from d tuples to there, every polynomial function that's invariant or equivariant under basis change, it can be written as a trace polynomial. So traces and words in x1, x2, they are the only things that are invariant on the base of change, after changing the basis. Right? Okay, you're going to say, well, but there are other functions like determinant, right? Determinant is always also stays invariant, but you can express determinant with traces. Right? Cayley-Hamilton theorem tells you that determinant of a matrix can be expressed with traces of a matrix. Okay, now also this talking about trace, like inequalities involving traces, that's also not, I mean, it's not completely stupid. So there's quantum information theory and free probability. These are two areas of mathematics that care about these inequalities. So I think in a few weeks, you're going to have David Jekyll giving a colloquium talk about free probability, and I have a feeling that he's also going to mention trace polynomials. Now I need to be careful a little bit where am I going to evaluate trace polynomials, because now I also need to evaluate a trace. So that means that I can't just plug in arbitrary operators, right? I want to plug in operators that have well-defined traces. So we're going to restrict to tracial von Neumann algebras. Right? So I mean, it's not too important what that is if you're not familiar with it. Okay, unital subalgebras when we can define a sensible trace on them. Trace that behaves like, for example, if you're in finite dimensions. So for example, think of matrices with the usual normalized trace. Well, normalized trace, so just taking 1 over n times the sum of diagonal terms. Why am I taking normalized trace? Well, as I said, I'm going to be talking about, I want to have normalized situation that trace of the identity is equal to 1. Why is that good? Well, because I'm going to talk about positivity in different sizes of matrices, so I kind of want to normalize that to make sense. Okay, now the obviously positive things now are, well, squares, right? These Hermitian squares, that was already before, but now what's also obviously positive, trace of a square. If I take a p times p star, if I take if I take a trace polynomial p, I take p times p star, trace of that, it's also going to be positive everywhere. It's kind of, I'm getting some more building blocks of positivity. Now to a constraint, now if I have some constraints, again, I'm going to talk about n times n matrices satisfying that constraints. I'm going to talk about all matrices satisfying that constraints, and I'm going to talk about operators satisfying those constraints. It's just that now, as I said, because I need to evaluate trace, I'm just going to restrict to operators coming from von Neumann algebras, so that trace is going to be well defined. And now, because I have an additional building block, traces, I also need to fix my quadratic module definition, right? So before quadratic module was what? Well, it was something that was closed under addition, and this kind of a squaring, like multiplying with p and p star from the sides. What I also need in addition is that the trace of a quadratic module, trace preserves the quadratic module. Well, because you kind of want to simulate that if you have something positive, well, trace of that thing should also be positive. So I need to add a bit more things. Okay, and once you have that, things fall in place. So now Prochisi and Shachar already proved that if you add these traces, then you can kind of describe positivity on n times n matrices using sums of squares and their traces. So if I allow also traces of square, then I can certify in an algebraic way that some trace polynomial is positive semi-definite for all matrices of all sizes. We also have the same, well, equally good result in a bounded situation. Now I'm going to skip that because I'm running out of time. To finish, let me just go back to infinite dimension. So how I started was, first I talked about free polynomials in the dimensional free setting. Then I said, well, when I go to fixed size, it's kind of annoying. Then I took a bit more functions, I added traces, then it became nice. And now I'm going to go to the I'm going to go back to the dimension free setting. So again, all matrices or all operators. And here it's not going to work. So this works nicely for free polynomials. It breaks down for trace polynomials. And the reason is, I wanted to mention that before I finish. So Kuhn's embedding conjecture. So I know if you heard this year, Kuhn's embedding conjecture got refuted. So it was a conjecture, what, 30 years, no, almost 50 years old. It got refuted. And it's an important conjecture, right? I mean, it plays, it has several interpretations. And one of the interpretations, it's actually interesting for us. So the fact that Kuhn's embedding conjecture fails is equivalent to the following. It means that there exists some free polynomial f such that it's going to have positive traces whenever I plug in any symmetric contractions, metric contractions. However, there's going to be some self-adjoint operators from a von Neumann algebra that when I plug them in this polynomial, the trace is going to be negative. Okay. So when I'm in a constrained situation, so I talked about contractions, right? So that's a constrained situation. It's kind of, I have a disparity between talking about matrices of all sizes and operators. So that means that here I'm going to be struggling getting some nice sum of squared certificates for all matrices, because if I have a sums of squared certificates, it's also going to work for operators. So I can't have one for all matrices because these two situations are not equivalent. Okay, I should just mention that we do have an answer. We do have an answer for operators. So for operators, for certifying positivity of trace polynomials on operators, we do have a certificate in terms of quadratic modules in a bounded case, in an Archimedean case. However, for the global case, like being positive on all operators, that's open. We don't know. I mean, if I have a trace polynomial that's positive on all matrices, is that the same as being positive on all operators from von Neumann algebras? I don't know if that can be certified using sums of Hermitian squares and traces. The only thing that I know, and that James come into that, so let me finish really with this result for today. We do know that that's true in one variable. So in one variable, meaning that I just have variable x and polynomials in x and in traces of x and traces of x squared. So whenever you have expressions made out of these guys, then positivity on all matrices is really means that I can represent this polynomial f in terms of sums of Hermitian squares. So in this case, geometry and algebra really play together. So to sum up, we kind of have this kind of a situation. We have results for free polynomials, we have results for trace polynomials. In each of the case, we can talk about global or bounded situations, so bounded meaning some constraints, and you can talk about positivity on matrices of fixed size, matrices of all sizes, and operators. And here the ticks are for the good results, crosses are for bad results, and questions are for, well, open questions. Okay, and sorry for running over time, but thank you. Thank you.
Okay, are there questions for Jurij? So I'm not seeing in the chat or anyone speaking up, unmuting themselves.
Oh, sorry, yeah, I don't see the chat. Yeah, so.
Yeah, otherwise I would have alerted you if there was something there. Anyways, well, we should all thank Jurij. I'm clapping for him now. Okay, so we'll maybe stick on for a few minutes if people have questions they want to ask, discuss.